Okay, so we already talked about 2 by 2 determinants. Of course, you're simply going to be AD minus BC. Okay, a 3 by 3, I personally enjoy, and have always made sense to me. Expansion by minors, and so I like that. I like it because I also use that when I do cross products. So it goes like this. Always minus on the second one, and it alternates. So get rid of B's column and its row, and you're left with these guys that are not in its row and not in its column. And then plus C, going to be DEGH. And then it'd simply be a matter of cross multiplying. So EI minus FH, B, and this DI minus FG plus C, DH minus GE. Okay, and that's great. My son, when he went to college, learned determinants, and he came home and was asking me a question. He's like, in the middle of the test, I couldn't remember how to do this problem. It kind of pissed me off. He says, couldn't really, and the way his teacher made him memorize it was he made him memorize for the 3 by 3. He made him memorize this, and I'm like, nah. He's like, yes, that's how they made us memorize. I'm like, well, that's stupid. I can't remember that. So I showed him expansion by minors. This just factors back into this. You see that? And then that comes from there, and that's how I learned it. Okay. Again, I like it for when I'm doing cross products. That's a place where it comes into mind. So if I have this vector 2, 5, 6, and the vector 3, 1, 7, and I would like to find their cross product, I just take I times 5, 6, 1, 7 minus J, 2, 6, 3, 7 plus K, 2, 5, 3, 1, and then I get 35 minus 6 is 29I, and then I get 14 minus 18 is negative 4, so plus 4J. And 2 minus 15 is negative 13K. And that is how I like to do my cross products. It's just expansion by minors. All right. Another way to do a 3 by 3 is to recopy the first 2 columns. And this only works for a 3 by 3. Okay. So it's why I never liked it, because like, oh, great, it works for one thing. But it's pretty slick. You multiply these guys, and then these guys, and these guys, and then you subtract these ones, and those ones, you get the exact same thing you had before. And again, it only works because you ended up with A times E times I, which is A, E, and I right there. You with me? So that's negative 8. And then it's 14, that's 56 times 2 is 112. And then it's 18. And going the other way, you're going to have negative 48. But it's already negative, so it's going to be positive 48. Minus 7. Minus 48 again, I guess, right? That's handy. And so, I feel like this and this is negative 15, so that gives you a positive 3. So 115 should be your answer. Okay, and that would be it. So it's cool, it works nice. Once you get past a 3 by 3, kind of have to do expansion by minors. And no, it's not terribly fun. No one said it would be. Life isn't fun, babe. The old man used to say that, or something akin to that, anyways. Whatever, don't care. So I take 1 times this dude. Minus 2 plus 1 minus 4 and then you got to expand by minors again. Ugh. So it'd be 0 times this guy which is just going to be 0 again, so that's cute. Minus 2 times, and then look, this is kind of neat because what do you see here? It should be 0 as well, right? And then plus 1, that one's actually going to amount to something. Minus 2, and 1, this one of course is going to be 0 as well. That's pretty neat. Plus, or minus 2, 0, 0, 2, 0. That's also going to be 0. And then, of course, plus 1, 0, 1, 2, negative 1. That one's actually going to amount to something. Aren't it? That's going to be 0. 0 times anything is 0, but it'll also be 0 inside. Plus 1, 0, 1, 2, 3. Stop it. And then minus 4. And of course this one here is going to be 0, so whatever. And then plus 2, 0, 1, 2, 3. Gross. Okay? A little bit at a time. That's how you eat an elephant, one bite at a time. So this is 0. This is 0. And then this is negative 1 minus 3 is negative 4. Times 1 is negative 4. Times 1 is negative 4. Cool. And then here you're going to have 0, 0, and then 0, minus 2, negative 2, negative 2, positive 4. That's cute. And then, and then minus 2, so plus, minus 2 times 1 is not minus 2. And then, lastly, but not leastly, negative 1 minus 3 is negative 4. So negative 4. And then you're going to have 0. That's handy. And then you're going to have minus 2 times 2 is negative 4. And then times negative 4. So negative 4 is negative 8. Times negative 4 is positive 32. So 30 should be our answer. Okay. Ugh, let's see if we did it right. I'm almost afraid to ask. Sometimes you just like, if I do it, do I look? Do I bother to look? I don't know. Sometimes you're just happily ignorant. I'd like to play one of those people that just doesn't care anymore. Just like, I just don't care, man. I got it done, didn't I? I'm going a little bonkers. I don't get to talk to anybody anymore, and it's kind of weird, and I'm getting a little stir crazy, and yeah. What did you do wrong, stupid? What did you type in wrong? Did you type something in stupid? You did, you big dope. Get too many commas in there. Nope. Look at that. Another one there. Boy, what is wrong with me today? Well, where do you want us to start, Jay? 30. Is that what I got? I feel like that sounded right. By God, it is. Nice. All right. So expansion by minors. It's tedious, but it always works. Okay. So it's, you know, it's not terrible. It's fine. It's, you know, it's okay. I don't know that it's great. The way the book talks, your book refers to it. Laplace came up with that. But that's his expansion by minors routine. Okay. So there's a couple other little tricks to these guys and some terminologies. So let's just see what's what here. What would happen if I took that same matrix? Gross. Here it is. Okay. And interestingly enough, you're like, well, actually, I'm going to hold that thought. I'm going to do it on a smaller matrix. I don't want to do it on such a big one. So let's go through a few things. So first of all, if there's any time there's a 0 row, so if A is n by n, okay, and if A has a 0 row, if A has a 0 row or column, the determinant of A is equal to 0 every time. Now, two reasons for that, but the big reason is this. If you had this, Does this matrix have full rank? No. If it does not have full rank, you have a 0 determinant every single time. Every time. Okay, that's number one. Number two. If B is obtained by interchanging two rows or columns of A, then the determinant of B is equal to the negative determinant of A. So if B is found by swapping two rows or two columns, doesn't matter, whichever, then the determinant of B is equal to the negative determinant of A. Okay? And let's just do one here. And we'll just show you what we mean by that. Oops, what are you doing, Danny? There you go. Now, what if I did the following? Did 4, 5, 1. Negative 21. Yay! I just swapped those last two columns. Okay. Yeah. That's just all there is to that. Okay. If A has two identical rows or columns, the determinant of A is 0. If A has two identical rows or columns. Now again, remember, what is that saying to me? It's saying the thing does not have full rank because obviously those two are linear combinations. So the determinant of A is 0 every single time. If B is obtained by multiplying a row or a column of A by K, the determinant of A, the determinant of B is equal to K times the determinant of B. Yes. So if B is obtained by multiplying one row or column of A by a constant K, the determinant of B is equal to K times the determinant of A. That's always true. Okay? If A, B, and C are identical, except the ith row or column is the sum of the ith rows of A and B, the determinant of C is equal to the determinant of A plus the determinant of B. Okay? You're like, what the heck does that mean, Jay? Let me demonstrate, sir, ma'am. If this is A, this is B, and this is C. Check it out. Oops, wait, sorry. A, B, and C are identical except for the ith row. Sorry, my bad. Got a little carried away there. Okay? What we're saying here is that the sum, or this row here, is the sum of these two rows. Are you with me? So let's see if this is true. So that's going to be 4 plus 4 minus 21, rather. So negative 17. This is going to be 12 minus 56. Good Lord, that's 44. Must be 16 minus 77 is 61. Hey, lo and behold, this plus this is that. Yay! That's cool. Don't use that one very often. I'm not gonna lie. If B is obtained by multiplying one row of A to another column, by multiplying one row or column of A to another row or column, the determinant of B well, by adding a multiple of one row or column to another row, then the determinant of B is equal to the determinant of A. Interesting. Okay, so what does that mean? Okay, well, let's find out. Okay, let's say this is my A. So let's find our B. So B, it says if you add a multiple of one row to another row. All right, cool. So let's take 2R1 and let's add it to R2, shall we? Just for fun. Let's just put it. It doesn't matter where I put it. Let's put it in R2, shall we? So it's going to be 6 plus 4 is 10. It's going to be 4. That's going to be 12. It's going to be 21, I think. And then 8, 1, 7 didn't change. Look what's going to happen. So I'm just going to use a calculator to find these determinants here because, well, I'm in a hurry. I'm going to do it right. I don't want to screw you, waste your time more than I already have, of course. Cool. Negative 13. Kaboom! All right, so those are some of the properties of the determinant. They're algebraic properties. Pretty easy to do. So if you had an element, so these ones follow straight from there. It's pretty straightforward. So if you have E be an elementary n by n matrix, so E is an elementary n by n elementary matrix. Okay, what is an elementary matrix, Jay? Ooh, now remember, that was given to us back in, where's the actual definition of that for you? That was back in, hang on a sec. So remember, an elementary matrix is any matrix that can be made when you start from the identity matrix, remember? And then what can you do to that? Well, you can add multiples of things to them. For instance, you could take 2R1 plus R3, and that would give you 2, 0, 1. And then you could do 3R2 plus R1. So 1, 3, 0, and so on. And then you can do whatever. And then you keep going, right? So that's an elementary matrix. Okay, so back to where we were. And where did I leave off? There you go. Here it is. So if E results from interchanging any two rows, then the determinant of E is negative 1. Okay? So, for instance, let's start with this guy right here. Ouch. Okay, let's see what happens here on this guy. Okay, now it's important to remember when you're doing these elementary, for this particular process that we're talking about here, they mean just adding, not multiplying by a constant. So for this particular formula, if I multiply by constants like I was going to do, then when you'd swap a row, obviously the determinant of B is equal to the negative determinant of A. Obviously, that's straightforward. However, when these are all zeros and ones, like for instance 1, 0, 1, 0, 1, 1, 1, 1, 0, for instance, if this is A, then when I flip-flop these guys, what do you expect to happen? We're like, well, it's going to be the opposite. Well, that's true, but let's see what happens here. So determinant of, I agree that it's going to be opposite, but again, this just follows from the other theorem. Oopsie daisy. Oopsie daisy. So the determinant of our A here is, okay, there it is. Yep. Oh, duh. So did I have one where I had two? Interesting. Yes, okay. So it must have had one doubled up somewhere. I don't know. Something went really weird there. Anyway, so what it's saying is if you flip-flop these rows, you're going to get the opposite. You're going to get negative of what you had. Well, that's pretty clear, okay? What would happen if you had just numbers, just stuff on the diagonals? In other words, you had K, in other words, very similar to where you had the eigenvalues on the diagonals or something like that. So, for instance, if you had this, what if you had, I don't know, 2, 0, 0, and then you had, you had 0, 5, 0, and then on the bottom row you had, dummy, what are you doing? 0, 0, 3. I'm telling you that I think it's going to be 30. Too many variables. Oh, I know what happened. Didn't put a do-who. No, don't shut off. Oh, freaking computers. I got 3 of them going right now. It's freaking me out. There it is. And what is that? Well, it's because it's just the product down the diagonals. Okay? And it makes sense because it's going to be 2 times this little square matrix down here with 5, 0, 0, 3 in it, right? And then it's going to be minus 0 times those guys, which is going to be 0, plus 0 times these guys, 0. Okay? And so in that situation, boom, you're done. Piece of cake. Okay? What happens, by the way, just for fun here, what happens if you have a triangular matrix that looked like this? Oops, stupid idiot. Okay? Or it's an upper triangular matrix, yes? When if you had one of these guys, what would your determinant be? Would it be 3 minus 6 times, well, now look, that's going to be 0, right? Plus 1 times 0, 4, 0, 0. And so it's always true, by the way, that a triangular matrix will always give you a determinant. The determinant of a triangular matrix, whether it's upper or lower, by the way, will always be the product of the II all the way down the line. So it'd be the product of those guys. And I have to think about how to write that for a minute. It'd be the product. I goes from 1 to n of AII. In other words, it's just the diagonals. 3 times 4 times 4. Done. Okay? That's always true on any triangular matrix. Always. Okay? Right. A square matrix, this is a big deal. A square matrix is invertible, or in other words, is invertible. In other words, it has an inverse if and only if the determinant of a, so a square matrix A, put that way, determinant of A does not equal 0. Okay, and why is that? Because the inverse, for instance, will always be, so A inverse will always have 1 over the determinant of A times the rest of the matrix. Well, if this is 0, we're screwed, yes? Okay, why wouldn't it be invertible? Well, we already talked about this. If 2 of the rows are identical, or 2 columns, doesn't matter, or if this guy is a linear combination of the 2 above it or something, okay, well then you do not have independent situations. Those are all, remember, those are all equations, and if those equations are not independent, then there will not be a solution. Now, does that mean that they're parallel or perpendicular, or parallel, or they are the same? It doesn't matter. There's still no solution. Okay, and why is that? Because the determinant will be 0. It's a big deal. Me personally, I think that's probably the easiest for me to remember. If you take, so again, our buddy A is just a square matrix. If you took K, which is just any constant, and multiplied it to it, the determinant of A of k times a rather, is equal to k to the nth power times the determinant of a. Remember, a is an n by n matrix. Okay? So you're not sure you buy that? I don't know. Let's find out. Oh, let's see. Let's do it this way for fun, huh? So 1 plus 0 plus 1, and then it's going to be minus 1 minus 0 minus 0. So the answer is 1. Yay! Now, had those all been k's, you'd have k, 0, k, 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 0, k, k. That is just not cool. Didn't even think about that aspect of it. Weird. Don't care. It's just odd. Look what we have here. We got k cubed. We got plus 0, obviously. We got another k cubed here. Cool, whatever. And then we got minus k cubed. We're going to have minus 0 and minus 0. And so those cancel off, and lo and behold, you get k cubed. In other words, k cubed, or k to the nth power, times 1, which is what the determinant was previously. Weird. Okay. These are just some of the ones that it's pretty straightforward. If a and b are n by n, a and b are n by n. And if you take a times b, of course, it is also n by n, right? Then the determinant of a times b is equal to the determinant of a times the determinant of b. Okay? Fact. The determinant of a inverse is equal to 1 over the determinant of a. The determinant of a is equal to the determinant of a transpose. Meaning you flip the rows and columns around, you're multiplying the same things, you're just doing it in a different order. Okay? And I want to show you one more that you can impress the ladies at the bar with, I guess. You're like, oh, dude, I got to solve this equation. Now, I only have 87 ways to solve it. I mean, literally, our teachers have taught us like a million ways to solve this problem. So, 119, cool. But I'm going to do it this other way. Okay, there is a different way to solve this problem. It's called Kramer's rule. Okay, and to do Kramer's rule, what you do is in your denominator. So x will equal, and it's a determinant divided by a determinant. Okay, and so what you're going to end up doing is the following. You're going to replace, for x, you're going to replace the x column with the answer matrix, with the answer column. And then on the bottom, you're always going to have the original A matrix that we normally start with. Okay? So this is going to be 63 minus 38 over 27 minus 2. So that's 25 over 25, which is 1. For y, you would do 3, 1, 7, 19. Again, replace the y's with the answers. The bottom stays the same, which means the bottom is just 25 still. The top is going to be 57 minus 7 is 50. 50 divided by 25 is 2. Ta-da! Your answer is 1 and 2. Okay? It works. You know, do you know why it works? No. Have I proved it at some point in my life? I have. Do I remember why? No, not really. Is it a big deal to me? No, not really. So just be aware of that. There is one more thing I want to show you, and that is that you can expand by any column, okay, or by any row. It makes no difference. So I want to do one of those. Just want to show you that you can expand by minors differently if you wish. 3, 6, 1, 2, 9, 8, 0, 1, 1, whatever. So if I do it the conventional way, I'll get this. And I will get, it's 9 minus 8 is 1 times 3. I get 2, 0, so minus 12. And this is 2, so plus 2. So -7, I guess. Okay? But what would happen? Because this first column has a 0 in it, dog. So what if I did that? What if I did 3? Now, if you cross out 3 row and column, we're still looking at the exact same determinant for 3. So that's 9 and 8, 1 and 1. Minus, now let's do the 2. Now who's the 2 messed up with? The 2 is going to be messed up with 6 and 1 and 1 and 1. And the 0, and it's 6 and 1 and 9 and 8. Of course, this is 0. Here you're going to get 6 minus 1 is 5. Times 2 is minus 10. 9 minus 8 is 1. So 9 minus 8 is 1. So 3. 3 minus 10 is negative. What? That's right, friends. You can actually expand off of any row or any column you like. Okay? Wait, does that also work? You said, Jay. I remember you hearing it. Okay? If one were to do this, well, actually, let's make it not a 1. Let's make this, let's do this one, yeah, because it'd be pretty neat. Let's watch. So you just go, okay, so 4, 3, 1, 1, 0, minus 9, 2, 1, 0, 0, and then plus 2, 2, 3, 0, 1. So that's going to be 0 minus 1, negative 1, so negative 4. This one goes away. This one is 2 times 2 is 4. The answer is 0. I'm like, oh, sweet. That's awesome. But what if you expand on the bottom row instead? So it'd be 0 times 9, 2, 3, 1. Minus 1. And then it'd be 4, 2, 2, 1. Right? And then it would be plus 0 times 4, 9, 2, 3. Of course, this one goes away because the time is by 0. So does this one. And then you get 4 minus 4 is 0. Hot diggity dang. Look at that at 0. So that's a kind of a convenient deal. That in the 21st century where, you know, we have computers to help us and calculators to help us do these things, it's not as big a deal. But I remember back in the day when I learned that, I'm like, you've got to be kidding me. I was scouting around. Heck, I was using the second row and expanding off the second row. It works. It's fine. It's just, you know, whatever. But once you realize that back in the day, man, you saved yourself a lot of time. And I never used the slide rule because I was not that old. But when I found out that you could save a lot of time and headache, boy, I just all over that crap.